Your line is now muted.
Good afternoon, everyone. Thank you for attending the third webinar in the Zero Energy Ready Home series on the Energy Star program. This webinar will be recorded and the recording will be sent out to all attendees. If there are any issues with audio, I posted a link in the chat for downloading the WebEx application, and hopefully that resolves your issues. But if not, feel free to message me privately. My name is Erica DeLello. I'm a project manager for NORESCO. This series is sponsored by the Colorado Energy Office and the High Country Conservation Center. And Jess Hoover is here to tell you a little bit more about that organization. I'll go ahead and unmute you, Jess.
Thanks, Erica. Hi, everyone. Good afternoon, and thank you so much for joining us today. As Erica mentioned, my name is Jess Hoover, and I am the Climate Action Director for the High Country Conservation Center. We are a resource conservation nonprofit up in Summit County, and we have been very involved in supporting our community's new sustainable building codes. We provide all of the energy consulting services that you can see here listed on this slide to assist our local building professionals. And we've been organizing educational workshops like this one to help folks learn what's required by the new code. We've also partnered with the Colorado Energy Office, Energy Smart Colorado, and Deeper Green Consulting to sponsor a local HERS Rater training course so that we've got new HERS Raters ready to support your building projects come July 1 when the codes go into effect. We're very happy to support building professionals in our community with code compliance, so we thank you again so much for joining us today. Thanks, Erica.
Great, thank you, Jess. So as she mentioned, NORESCO and Build Tank has been working with the Colorado Energy Office to provide trainings just like this one. But in addition to the trainings, we've also put together a code adoption toolkit that reviews cost implications, changing of code cycles, the benefits, other compliance resources, and a lot of other things. And then now we're currently working on a troubleshooting guide for IECC 2018 that will cover I-code conflicts, alignments, clarifications, and passive compliance. So that will be posted to the Colorado Energy Office's website shortly, but if you could please take some time to review those resources when they are posted and provide feedback to me if there's other information that you could use. On the next slide, this is a list of the upcoming trainings as well, and you'll see the Zero Energy Ready Home series and a PV webinar directed towards mountain communities. That's actually tomorrow. And then if you do have any projects in Denver County, there are also specific trainings available on those amendments. At the end of this presentation, I'll be sending you all a short survey with links to all of these trainings and the resources. If you could please take the time to answer these survey questions, it will help us continue to provide these trainings. I have muted everyone's lines to reduce background noise. Sometimes WebEx does like to act up, so please mute your line on your end as well. We do want to encourage questions, so if you could use the chat function, I will let our presenter know at the end of the presentation, and that will allow for time for discussion. So with that, we have Robbie Schwartz as our presenter today, and he's been a champion of the building science industry for over 20 years. As principal of Build Tank Incorporated, Robbie works with builders of all sizes to ensure that their high-performance homes are efficient, healthy, and resilient. So I'll let Robbie take the lead from here.
Thank you very much, Jess and Erica. Appreciate it. We have a lot to do today. This outline here is short, but the material is dense and there's a lot of it, so we're just going to jump right in. Like Erica mentioned, please type in the chat area if you have questions, and we will look at those at the end here. So these, again, are the 7 mandatory requirements of the DOE Zero Energy Ready Home program. Today, we're going to be primarily focusing on the Energy Star for Homes baseline and what that means, talking about how to achieve that rock-solid building thermal envelope, and talking about mechanical systems. So these first 3 main components. We did touch on the Energy Star Compliance HERS target score in the last session as well, and we'll touch on that just briefly here. So basically, to get to a zero energy home or zero energy ready home, again, we want to emphasize that you need to start very early in the planning process and goal setting process for your houses. So that's a super important part to remember. And I really applaud all those that are taking part in these series, because that's part of the process. Understanding what you need to do is part of that process, and setting the proper goals and expectations for creating that successful project that meets the requirements of the program and the code moving forward. Optimizing the building shape and orientation is something that the program really isn't that specific on. So if you're really trying to create a zero energy home, taking into account passive solar orientation becomes very important. But this program is really about trying to get yourself ready to be zero energy in essence in any orientation that building is going to see. So although it is a cost-effective way to get to zero, it's not something that the program itself highlights here. However, designing that high-performance envelope is something that's very important to the program and is the bulk of what we're going to be talking about today. Mechanical systems we'll be talking about a little bit today as well, and then ultimately commissioning or verifying and using that third party that we talked about last time. We'll review and show how that's done in the context of the Energy Star program and its link to the, sorry, that popped up here, link to the, here we go. I'm sorry, linked to the Energy Star program as well. So what is Energy Star, and how do we think about Energy Star? One way I like to describe the Energy Star program is to use an example of a refrigerator. So in the 1950s, a refrigerator was fairly small, around 9 cubic feet, and used a very small amount of energy, really. In the 1970s, things began to change. We started to move to the suburbs, and you can see that our refrigerators got bigger. The color changed pretty dramatically, and also the energy use for that refrigerator grew pretty substantially. And then in our modern day era, our refrigerators got even bigger. Now I've seen advertisements for up to 32 cubic feet refrigerators. We're going to Costco once a week or the store once a week, and we need to be able to store all of that food and whatnot in our refrigerators. But look what's happened to the energy usage of these larger and larger refrigerators, that it's really come down pretty substantial, and it's pretty much in comparison to that 1950 refrigerator. So in a nutshell, what Energy Star is a program that creates an energy specification for how to build a product that is deemed to be energy efficient. So it doesn't matter if that product is a refrigerator, a computer, a light bulb, a dishwasher, or a house. They create that specification for how to build that product successfully. And what we need to know about Energy Star is that you don't necessarily have to use Energy Star products to build an Energy Star house. The specification points that out. However, when it's combined with the DOE Zero Energy Ready Home program, some Energy Star products are required in that building of that Energy Star house. And we'll talk about those in a little bit here. So the Zero Energy Ready Home program requires that products and projects be certified under the Energy Star Home program using specific versions. So in essence, you need to use the most recent version that's applicable for your state or location, and we'll talk about that. Basically in Colorado, that's Energy Star version 3, revision 10. And then you would use a separate version of the program if you're doing multifamily programs. if you are also doing other programs that are optional, you would potentially be using Passive House or those things, and you want to use the most recent versions of those programs as well. Now, Energy Star partnership is an important thing to consider as well. In the same way that you're partnering with the DOE Zero Energy Ready Home program, it's important to also go through that partnership process with the Energy Star program as well, so that you can get full advantage of all the different support mechanisms, marketing mechanisms, logos, and all those things that you can get access to if you are a partner with the Energy Star program. So make sure you go through that process and become a partner with the Energy Star program. The Energy Star documentation is basically focused around a series of checklists that the program has. So the first checklist is an HVAC design report. Then you have the Rater HVAC design review checklist, and then the HVAC commissioning checklist that the HVAC contractor would do. Now, the HVAC design report and the HVAC commissioning checklist can be done by the same entity, but often we see that the design of the HVAC system is done by one contractor or one specialty, and the commissioning or installation of the system is done by a different contractor. And so there are two different checklists, and if the contractor, well, ultimately the contractor that is doing the installation and the HVAC commissioning also has to be credentialed, which we'll talk about in a few minutes, credentialed with the Energy Star program. There's a Rater field checklist that includes envelope details and HVAC commissioning or verification features. And then the last one is a builder water management checklist that needs to be integrated into the process here. All of these checklists we will go through in depth in this training today. Verification is also a mandatory requirement of the Energy Star program, and hence also a mandatory requirement of the Zero Energy Ready Home process in order to earn the Energy Star label and the Zero Energy Ready Home certification. These features need to be verified by a third party. So if an item on the Rater checklist can't be inspected, the home cannot actually earn the Energy Star label and therefore the DOE certificate. So coordination with your third-party verification organization is very important to make sure that that verifier is in the house at the right time and is not impacting your construction schedule, and that everything can be verified not only for compliance with the Energy Star program, the DOE program, but also in this case for code compliance. If a rater is not able to determine whether an item is consistent with the intent of the checklist, then the rater has resources that they can go to get answers to those questions. The first thing they would go to is their provider, and second of all, they could go directly to the Energy Star program to get further clarification and guidance on those details. But ideally, a lot of those questions would happen in the design phase for that house and those design charrette meetings that might happen early on in the process, so that when we get into the actual construction of the house, none of those questions would be had. Our ultimate goal here is to create this documentation for the Energy Star program, which includes the Energy Star label that is posted in the house, ideally in the electrical panel, but somewhere else. The idea is that this Energy Star label moves with the house. It's something that consistently says this house has been labeled as an Energy Star home, and for resale purposes and education purposes, that label stays with the house, whereas the certificate goes to the current owner of the house. It may or may not travel with the house as it changes owners, but the label would stay with the house during that process. Energy Star version 3, revision 10. So we want to make sure that we're using the correct version for your state, and for our state here in Colorado, because we are a home rule state, each jurisdiction has its own codes and standards. We utilize the version 3, revision 10. So why are there revisions? So Energy Star recognizes that significant efficiency above standard construction practices are happening, and that they want to stay ahead of code development, so they continually revise the system. Also, energy codes are becoming more stringent, and therefore, again, Energy Star wants to stay relevant, and therefore they'll do revisions. And ultimately, the revisions help clarify things, they help simplify things, and they ultimately improve the process of certifying a house to the Energy Star program there. So to continually improve that value proposition, Energy Star creates these guidelines that are regularly updated that include building science practices that can help improve the comfort of our homes, the indoor air quality of our homes, and ultimately the durability of all homes that are certified through the program here. And that's why it's really important to use the right revisions of these programs. Getting to Energy Star, getting to the Zero Energy Star or Zero Energy Ready Home certification, we want to go through these processes. So we need to determine eligibility to earn the Energy Star and the Zero Energy certification. That ultimately happens through this modeling exercise at the beginning of the process to set that HERS target score. We want to configure the energy efficiency measures in that house and use that rating software to develop that score. We need to complete and verify the items on these Energy Star checklists, which include at a minimum a rough pre-drywall inspection. So usually at a minimum you would do an inspection after insulation and before drywall, but sometimes you're doing rough framing inspections before drywall as well. So it might be a 3 or 4 part inspection process depending on how you've detailed things out and how you're working with your third-party verification group, which is generally a rater. And then that would also include that final inspection and blower door testing at the end of the process. We need to provide reports to the EPA and the DOE. These help generate the Energy Star certificates and label, and also the labels for the DOE Zero Energy Ready Home program. We need to provide and distribute those labels and certificates to the home buyers, to, in this case, code officials and other pertinent parties here, and then ultimately affix that label to the circuit breaker box or somehow that's some permanent location in the home. I've also seen those labels affixed to HVAC equipment or other things that will be permanent to that house here. So we remember to set that HERS target score. We're using this twin house modeling process where we enter the home's geometry into the house. The software creates 2 homes that are geometric twins of the house. We have the reference home here that's based off of the DOE Zero Energy Ready Home program. And so this supersedes the Energy Star reference home. Is superseded by the DOE reference home, so you'll get a slightly, in essence, more stringent HERS index target than you would for the Energy Star program if you were just doing that program by itself here. But again, the builder's house is compared to the DOE Zero Energy reference design to create that HERS index score target home, and the home that you built needs to be less than or equal to the HERS index score that is created through this process. So for Energy Star homes in general, here on the Front Range anyway, a HERS target for Energy Star is somewhere in that 70 HERS target range, and for the DOE program, it's somewhere in the 55 range. So you see there's a significant increase in the quality and performance of the thermal envelope and mechanical systems in order to lower that target score there. Verifying eligibility. So to pursue the Energy Star certification, we need to figure out which type of dwelling units are being verified out there. Are you doing a single family home or some type of multifamily structure here? And there are slightly different programs for each of those structures, but you can do verification for Energy Star and the DOE Zero Energy program, making sure that you pick the right programs that you're working with. Just a quick note on these overlapping requirements. Where overlapping requirements for code or the DOE Zero Energy Ready Home program exceed those that the Energy Star program have, the most stringent requirements shall be met. So sometimes you'll have to look at requirements for different programs, especially in a program like the DOE program, where the DOE is utilizing Energy Star structure and a lot of their requirements, but in some cases, the DOE program is going beyond what Energy Star requires. And that's seen at the starting point with the creation of that HERS index target baseline score that needs to be achieved. Where overlapping requirements conflict with the Energy Star requirements, the conflicting Energy requirement may be waived, and then waived Energy Star requirements may have to be approved by program administrators. So when you're waiving a requirement, you need to do some analysis to ensure that that requirement isn't detrimental to the program, that's being superseded by something that's more stringent, that you're not just getting rid of a requirement that otherwise would be required by the program for certification here. The Energy Star Home. So in its essence, we have these core energy features. We have the quantifiable energy use that we're getting through that HERS index qualifying process, and we have that solid building thermal envelope. We're including or adding to that this complete thermal enclosure system, heating and cooling systems in our houses, water management systems in our houses, and this idea of adding applied building science and systems thinking to the process so that we get a house that is, has total performance in it that equals Energy Star performance and peace of mind, enduring quality, wall-to-wall comfort, proven value, and efficiency. And we're taking all of these things and we're moving those into the Zero Energy Ready Home program here so that we're adding tighter construction, more complete air barrier systems, better insulation systems, advanced window technologies. We're getting ultimate control and predictability of airflow, thermal flow, and moisture flow. And we're getting a house that is ready to put PV on it to take it all the way that next step to zero energy here. So the combination of these two programs gives us a very significant requirement that will ensure that we get homes that will perform over time, that increase the value proposition of being ready to add solar to the process to create that zero energy home. Now, Energy Star, like I said earlier, Energy Star specifications aren't necessarily required by the Energy Star program, or what I'm ultimately saying is that Energy Star qualified products like appliances and fans and light bulbs and other things are not necessarily required for Energy Star, but there are some of those requirements for the DOE Zero Energy Ready Home program. Most significantly, Energy Star qualified fans are required for the DOE program. Energy Star qualified appliances are required, and Energy Star qualified lighting are required by the DOE Zero Energy Ready Home program there. And we'll talk more about that next week, actually, here. So let's dive into the actual checklists here. The version 3 revision 10 checklist. Now, the first thing you want to do is go to the Energy Star website. That's energystar.gov. Go to the New Homes program, partner with the program, and then download these checklists. And you need to spend some time with these checklists, and not just the checklist items, but also the footnotes in the checklist. The footnotes in the checklist become very important, not only for the Energy Star program, but for the DOE program as well. And you see in this case, the DOE Zero Energy Ready Home footnote 13 says that insulation levels in a home shall meet or exceed the component insulation requirements of the 2015 IECC. So these fenestration requirements for the Energy Star program and the insulation requirements for the program are actually superseded by the DOE Zero Energy Ready Home program requirements here, and we'll talk about those. But all insulation needs to achieve a grade 1 So let's dive a little bit deeper here. So windows being the biggest thermal hole in our envelope here, the DOE program is asking for a little bit more higher quality, better performing windows than the Energy Star program would. So windows have to meet the Energy Star product criteria listing in this table here, which we need to note is not the most recent version of the Energy Star qualification product criteria for Windows. They're using version 5 for Windows specification, where if you look out there in the marketplace, version 6 has been released out there. But the DOE program says that you have to use at least the version 5 Windows, which would be a 0.30 U value window at a minimum in our climate zone. You might be able to go higher than that U value depending on specific circumstances there. But at a minimum, you should try to get a 0.30 window in your home. There are some exceptions. You can do an area weighted average to determine that 0.30 window requirement. The area weighted average of all the fenestrations needs to be greater than or equal to 50% of the glazing shall be permitted to satisfy that solar heat requirement. 15 square feet of the glazing fenestration can actually be exempt altogether. So we might have a specialty glass or a glass in a front door or a door to the exterior that you might want to exempt from this, and you're allowed to do that. One-sided hinged opaque door assemblies up to 24 feet in area can be exempt as well. So pretty much most doorways to the outside, if they have glass components, can be exempt from this requirement. Ideally, although, you want to limit those exemptions because you're going to impact your overall thermal envelope through these exemptions. Passive solar glass can be exempt as well. So if you're going for the passive house certification, you might find assemblies that you need in order to take into account passive solar design, or you might be using triple glazed windows that aren't certified through the National Fenestration Rating Council, so there might not be a specific label for that window. So there's some ways to utilize those windows in this program as well. The DOE Zero Energy Program does recommend high performance windows that go beyond the 0.30 U value, and this thin film triple pane windows are an example of that. These windows performance can be as high as an R10 potentially, and that performance can significantly impact for the better the overall performance of the thermal envelope. But at a minimum, that 0.30 U value is what you need to keep in mind there. From a thermal envelope perspective, the DOE program relies on this statement that's in the IECC that basically says that R38 shall be deemed to satisfy the requirement of R49 wherever the full height of uncompressed 38 insulation extends over the wall top plate at the eaves. This ultimately means that you can lower the R value if you can still meet the HERS index target score there, as long as you, in essence, have a raised hill truss and enough insulation that goes fully over that top plate there. The picture on the right shows a raised hill truss that can receive an R38 and then a transition back to the R49 attic insulation requirement in most of these high altitude climate zones here. So that is probably a better way to do it, but the code does allow you to maintain that 38 continuously if you want to, and you can meet the other requirements here. Through performance calculations, you can break out the insulation on both over the top plate and over the main body of ventilated attic and do that type of calculation there. This exemption shall not apply if using the UA alternative calculations, however, there. So you would have to break that out separately there in those types of calculations. The field rater checklist exemption also says that for ceilings without attic spaces, R30 shall satisfy the requirement for any required value above R30 if the design of the roof ceiling can't accept more than that R30. You also have this 500 square feet exception as well. However, the installation still needs to be installed well, and you have to make a choice of if this assembly is going to be a vented assembly or an unvented assembly. And you need, if it is going to be a vented assembly, you need to ensure that you're separating that vent space from the insulation space to create a system that will work and perform properly. Again, the exemption can't apply if you're using an area-weighted alternative calculation, which is allowed by these programs here. Unvented attic assemblies can work as well there, and I just wanted to point that out, and we'll talk more about unvented attic assemblies at a later session here. So the National Rater Field Checklist allows you to use the IECC UA calculation to demonstrate compliance with the overall R values and U values that are required to meet the 2015 envelope requirements for this program. The insulation levels of fenestration, ceiling, walls, floors, slabs can be traded off in that calculation. And so that gives you the ability to add flexibility in how you want to build your home. You do those calculations using the softwares on the right side of this slide there. There is a caveat here. The insulation needs to be installed to a grade 1. Any trading off of insulation over the top plate can't be traded off below an R21, and any slab edge insulation trade-offs can't be traded off below an R5 there. So we're ensuring that there's at least some insulation over these locations, in these locations, and that insulation is being installed properly per manufacturer instructions and per the ResNet standards grade 1 install here. The UA calculation for all assemblies shall be done using, again, an approved method, which would be one of the softwares that are detailed out on the right of this slide here to be used to do that calculation. Now, the code leverages this statement that insulation in all systems, in essence, need to be installed in accordance with manufactured instructions. These programs, specifically the DOE Zero Energy Ready Home program, also includes that they have to be installed in accordance to ResNet grade 1 standards. So let's review real quick how insulation works. Remember that insulation, like this fleece jacket that this gentleman's wearing, is designed to trap a pocket of air. And it's really that stagnant pocket of air that's being trapped by the insulation product being used that is the source of the resistance of energy from hot to cold surfaces. So in this case, from his body to the ambient air outside. We also need an exterior air barrier system when we're talking about cavity insulation in walls and floors in order to get that stagnant pocket of air, because air will move through these fibrous materials. So you either have to use an air impermeable material, insulating material, or an air barrier system around air permeable insulation to get it to work. Now, the manufacturing instructions probably aren't read that often, but here's an example of the manufactured instructions that the code or the program base point would be looking for to ensure that we get these materials installed properly. But these programs goes further, and they look at the ResNet grading standard. This would be addendum or appendix A of the ANSI 301 standards where you'd find this. But in essence, it says in its first statement that insulation shall be installed to manufactured recommendations or installation instructions, in essence there. Then it gives some examples of those manufactured instructions. And then in the new addendum A or appendix A, they call out specific requirements for specific materials that are being installed. So they look at fiberglass bats and blown cellulose and fiberglass, and they look at blown foam products, and they call out specific installation requirements in order to get grade 1 for each of those requirements. These requirements are based off of compression, allowed compression, and allowed gaps and voids in the material. So in essence, to get a grade 1, it doesn't have to be installed absolutely perfect, but it has to be installed really well. Roughly 2% gaps or compressions and voids in the material are allowed, but that is basically being proven to not degrade the overall R value of the material that's being installed there. So you have to be able to install that. And the ultimate reason why is that if we get poor installation and we're trying to do energy modeling and predicting of the energy performance of that house, and we assume that a R19 bat was installed, but we actually get performance in the range of R7 or 4 because of poorly installed insulation, we're not going to have the right modeling, we're not going to have the right predictors for our other assemblies or for the overall performance of our houses there. And ultimately, that predicting is what's leading towards the certification of these houses for code, for program compliance with Energy Star, or the DOE Zero Energy Ready Home program here. And in order to get that great installation of the materials, the program creates this thermal enclosure checklist that the rater utilizes. So the first part of this checklist is looking at the alignment of air barrier systems with our thermal envelopes. So remember the continuity, strength, durability, stiffness, and impermeability, key requirements of air barrier systems here. So the code says that we have to have a continuous air barrier all the way around our house, that we can't use air permeable insulation as an air sealing mechanism, and these programs just pile on to the code, and in essence, the code has taken these requirements into it from programs like Energy Star and the Zero Energy Ready Home program. So you are still required to depict your thermal envelope around your, you're doing that basically that red line test. Put your pen on the paper of the elevation drawing of your house and continuously document where your thermal boundary is that separates conditioned space from unconditioned space. This section of the thermal enclosure checklist also helps better define how attic insulation works. We have requirements for eave baffles and attic insulation in ventilated attic spaces to be able to ensure that we're not getting wind intrusion into the insulation and we're not actually blowing insulation off of that top plate there. So the idea here is to get attic ventilation up and over the insulation, so that attic ventilation is when it's going to drop into our insulated attic systems here. It's dropping in from the top, and it's only circulating through the top, maybe third or quarter of the insulation, and not dropping into the insulation that's adjacent to the drywall below. That's our boundary between our conditioned space and unconditioned space here. So the programs are trying to ensure proper attic eave baffle installation, which is basically borrowing from the code language here. We have to install attic baffles. They need to maintain openings, and they need to maintain air circulation up and over the baths in every bay. So that is something that's a little bit different with the DOE program, that every bay needs to be baffled there. And we need to install those baffles correctly. So this is a picture of a system that's not installed correctly, where that baffle isn't coming down to the top plate. They've basically stuffed fiberglass bat into those locations, and that bat material doesn't stop the movement of air through it and or ensure that the air is going up between the baffle and the sheathing above here. So we want to always ensure proper installation. This section of the thermal enclosure checklist next deals with drop ceilings like this drop ceiling. It tells us that that drop ceiling, when you go into the attic and see something like this, it's not installed properly. We need to ensure that we get the sequencing correct, that we get the air barrier to the exterior wall installed first. We get air barriers to the bottom core of the truss. Then we do any overframing for a drop ceiling, which ultimately brings that drop ceiling into the conditioned space so that we can insulate over the top at the bottom core of the truss level there and make it work. And again, it brings that drop ceiling into the conditioned space of the house. When we have these drop ceilings and coppered ceilings, they become almost impossible to insulate properly unless you've detailed it right. And it's a reminder here that that sequencing is super important, and that about 90% of these air barrier details that are called out in code and called out by this thermal enclosure checklist are the responsibility of the framer. The framer needs to see it, needs to get that air barrier up first before they do overframing, and do it at the framing stage of construction, not at the insulation phase of the construction. That's true for air barriers behind tubs and showers and shower seats as well. Get the air barrier up first, then do the overframing for any tub surround or seating in tubs and showers. Make sure that all of that happens and happens properly, which means that you might have to pre-insulate if you're, depending on the material you're using, or you might have to provide access to blow insulation behind these air barrier systems that's shown in this picture up at the top here. Continuous air barriers at stairwells as well. So the drywall is going to come down to the top of the stair stringer. What's happening continuously past that stair stringer? What's happening underneath stairway platforms there on exterior walls? All these locations need to have proper air barriers. So in this case, you can see a piece of thermoply that was run long past the stair stringer so that the drywall will come and overlap that thermoply material on the top and bottom of this stair stringer to make sure that it's going to work. Behind fireplaces on exterior walls, again, get your air barrier up first, then do your overframing for the fireplace surround there. Knee walls are another. Any wall that's adjacent to an attic space, again, it's a sequencing problem. You need to get your top plate up, your bottom plate up, side studs up there. You're creating a true cavity insulation that's adjacent to the exterior in a ventilated attic. You have to put that attic side sheathing, and then your drywall would be the six-sided enclosure there. So you might be hearing more and more of that notion of six-sided enclosures when we're talking about cavity insulation. Again, insulation in our walls, in our floor systems, and potentially raftered attic assemblies or roof assemblies here. That would be another example of a six-sided enclosure. When we're talking about six-sided enclosures, we have to have enclosures that can actually be insulated. So we're seeing more and more truss systems define that attic knee wall between conditioned space and unconditioned space. This truss is not thick enough to be able to insulate properly. So you might have to either turn it on end or overframe that truss there, which is exemplified in this picture at this shaft wall for this skylight. So the truss system defines the shaft of the skylight, but it's been overframed so that it can be properly insulated. We've got a top plate, we've got attic side air barrier system installed. They still have to deal with that bottom plate issue and how they're going to detail that. And then drywall would be the sixth side of this assembly here to make it work. The Energy Star program calls out these small raised attic assemblies that create small knee walls. And in essence, we've created a 1-foot rule. So if you have a raised ceiling up into an attic that raises only about 1 foot, you can mount insulation over that and get an assembly that works pretty well. But if anything that's over a foot, you want to treat it like a true knee wall and get an air barrier on that attic side, and then extend that air barrier up so that insulation on the taller attic doesn't fall off over to the smaller attic there. So remember that 1 foot knee wall rule, and you'll be set there. Again, make choices. Define where the thermal barrier and boundary is going to be. Make sure that you have 6-sided enclosed assemblies, and that where you have to add supplemental air barrier systems behind fireplaces or at double walls, that's what you need to do. So there's a variety of different ways to handle double walls or shaft walls that are adjacent to exterior walls. You can fill the chase completely full of insulation. You can define the air barrier and thermal barrier system to the outside. You can define it to the inside, depending on the architecture here. But ensuring that you have that continuity of your air barrier and thermal barrier system, that continuity there, that's what these programs and codes are trying to determine here. Other places that sometimes cause problems are walls adjoining porch roof assemblies. If you haven't sheathed it completely, gotten your weather-resistant barrier, your air barrier systems up before you put on the roof assembly, that's defining that porch roof, you're going to have a problem. You're most likely going to have that floor system open to that roof assembly and have a non-compliant assembly here. So get the assemblies done correctly. Again, it's a framing issue, and it's the framer's responsibility. So we're going to have to do some education with the framers to make sure that we get these things right. Garage separating conditioned space from unconditioned space, that wall there's floor system over garage, there's floor system over the house. We need to separate and seal all those gaps between the systems there. The picture on the right shows a lot of these situations where it hasn't been sealed properly, so you might have to inspect and then get it fixed and re-inspect, depending on what happens during the third-party verification. Cantilevers are notoriously difficult to insulate, especially with fiberglass bats here. These systems ensure that we get that 6-sided enclosure, that we get fully insulated cantilevers that have alignment of the insulation with that subfloor, and then ideally fully filling it full of insulation there. We want to try to ensure that we don't have ducts or other large obstructions inside of these cantilevers. If you're using a forced air system, move the duct outside of these smaller cantilevers. And we have to remember that cantilevers can show up in strange locations, like in this is a cantilever into the garage, but we need to treat it like part of the thermal envelope, and also part of that separation between the garage and the house there as well. Rim joists are a key area of leakage, especially our low side leakage. We need to get a continuous air barrier at that rim board material here. Remember that sill seal is primarily a capillary break, so we have to seal that joint between the rim joist and the foundation, the rim board and the sill plate, and the rim board and the subfloor, as demonstrated in this sequencing photo here. Making sure that these 3 locations are sealed, because in this location, this is one of those locations where there's an exception to the cavity enclosure requirement there. So it has to have that rock solid air barrier to the outside in order for the insulation to work and work well. So you might consider spray foam in these locations specifically, but if you don't do spray foam, sealing in these 3 locations make a ton of sense. Now, reduced thermal bridging is the next part of this thermal enclosure checklist. We talked about for insulation in attics above and that R21 rule over the top plate. You can't trade off below R21. And then for slabs, you can't trade off below an R5 here. Now, let's think about other things. So what this section of the checklist is really trying to guard against is excessive framing and thermal bridging that's associated with excessive framing. And we have situations where a framer might think that two studs are good, well, maybe 6 studs are better. So we get up into 15 studs that's supporting a header. Well, we've got big problems happening there. So the program requirement says that you can use ICF forms. You can use SIP panels. You can use continuous insulation as a means to slow or stop thermal bridging through framing, or you can use a, before we go there, you can use a advanced framing package, which I'll show you here in just a second here. But also, this thermal bridging happens at attic platforms that support HVAC systems that might be in attics or other things that might be in attics. So this section includes proper insulation underneath attic platforms, and then it goes into the advanced framing package here. Now, the advanced framing package includes all of the following here. It includes insulated corners at exterior walls, so a 2 or 3 stud corner at these exterior walls, and where interior walls meet exterior walls, some type of insulated junction or corner at that location as well. It includes insulated headers. Insulated headers can be done if you use a 3-ply header using foam board installed there, or it can be done using a 2-ply header and foaming or insulating in that space that's provided there. But insulated headers are a mandatory requirement of it. And then it requires limiting the framing around windows and doors. Limiting the framing means that you have one pair of king stud per window opening, 1 pair of jack stud per window opening for supporting of that header. Additional jack studs shall be used only as needed for structural support. So it needs to be documented by your engineer that you need that additional framing member there. So it's not trying to create a structurally unsound house. It's just saying that the engineer needs to do their job and call out exactly how many king studs might be needed there. And then cripples only as needed here. And then moving away from that, you get into this discussion of 16-inch on center or 24-inch on center framing requirements. So in climate zones 6 through 8, a minimum stud spacing of 16-inch on center is permitted if you're doing 2x6 framing, if you have an R20 wall or better cavity insulation inside of that assembly. However, all 2x6 framing with stud spacing 16 inches on center needs to be installed regardless of any framing plan or alternative UA compliant approach that's used there. So in essence, you can't trade off if you're using less than R20, you can't trade off that R value there and not do 16 inches on center framing. If you're going to do a trade-off of your wall R value, which is very unlikely to be able to meet the program, you would have to go to 24-inch on center framing in essence here. You also have choices of going to a double wall assembly if you wanted, and this is just an example of what that looks like and some of the things that you need to think about if you're doing a double wall assembly here. So we're not going to spend much time here. Now, the slab edge insulation requirement and ensuring that you have a minimum of an R5 is the demonstration. This slide basically demonstrates why you need that. You've got a significant amount of heat loss through that slab at that slab edge here, so you want to make sure that you get that done and done correctly here. So you have a variety of different ways that you can insulate that slab edge to avoid that heat loss and that thermal bypass that's shown in the picture on the left here. You can insulate from the inside, you can insulate from the outside. We're seeing most builders that are doing a stem wall and slab poured separately just use insulation to replace the expansion joint that you would put there normally there. But ensure that that insulation travels all the way down from the sill plate or top of foundation wall all the way to your footing is recommended there to go all that depth there. But get that slab edge insulation. So the last thing the thermal closure checklist looks at is air sealing details. ensuring that we're not using air permeable insulation as an air sealing material. You can see all the problems that are associated with these pictures here, and most likely that the insulator didn't really know what their product could do and couldn't do in these locations. So it's also making sure that we get air barriers and air sealing done in the right locations here at shaft penetrations to unconditioned spaces. Again, it ultimately becomes a sequencing issue. So you need to install the air barrier first, then cut a right size hole through that air barrier, and then pass whatever you're going to pass through that air barrier system, and then ultimately seal it up and seal it up properly there. Again, a large onus goes to the framer to get that air barrier up first so that the other trade partners can cut the right size hole, and then other trade partners can seal it up properly here. HVAC boots that penetrate the thermal boundary have to be sealed from a code perspective. Energy Star and the DOE program take it a step further. If you're using a traditional forced air system, those HVAC boots need to be sealed to anything that they're penetrating in conditioned space or to unconditioned space. So through the subfloor, through the drywall, you have to seal that boot to that surface that it's being penetrated through. Other potential areas of air sealing that are required by these programs are around sump pits and sump pit lids and penetration through the sump pits, bath fan housing that has to be sealed to the drywall as well. Traps, plumbing traps need to be sealed and air sealed well. Spaces around window openings and door openings to framing are required to be sealed just like they are in the energy code. Electrical foam boxes, you have to use either airtight boxes or make non-airtight boxes airtight and seal those boxes to the drywall that they're penetrating there when they're on exterior walls or adjacent to unconditioned spaces there. You don't have to do the interior walls here. Again, another notion of electrical boxes that need to be sealed and made airtight. Airtight IC-rated can lights need to be used. Here's some example of some non-airtight can lights and why you don't want to use those, and then an example of airtight can lights. And we're seeing more and more of these LED can lights that are even more airtight than the traditional IC-rated can. But you have to ensure how are you going to seal the can light to the drywall. Often the gaskets don't work super well, so who's ultimately responsible? Whose scope of work is it going to be to do this additional air sealing of things that penetrate the drywall? So electrical boxes, fan housing, can lights. I think putting it into the painter scope of work makes sense, but you're going to have to make that decision and think about that before you start construction. The junction of the foundation and sill plate, again, crucial that that's air sealed, that the sill seal isn't your sole mechanism of air sealing. Again, that's mainly a capillary break. You've got to air seal that there and air seal it properly. This was an interesting new technique to basically do a Z sealing of that sill plate to the foundation. You can find this detail if you Google Steve Basic. He's an architect out of Texas that does a lot of very good details here. The junction of the top plate and the top of exterior walls that are adjacent to unconditioned spaces need to be air sealed here. So we're in this picture, we're looking down on a top plate, standing in an attic. You can see a large gaps between the top plate and the drywall, and the subsequent air leakage that turned this pink bat black because of so much air moving through the material here. So you can seal that top plate drywall connection on interior walls and exterior walls using sill seal, gasketing materials, or caulk type materials that are flexible caulking materials, often acoustical caulks, or that blue is a product called EcoSeal that is a flexible caulking gasketing member as well. You can also seal this from the attic as well. Sometimes it gets really difficult to get that air sealing out at the attic eave location, those top plate locations over the attic eave, but some builders and some designs make it very much easier to just do it from the top side as well. What we're ultimately guarding against is that these materials be, especially the gasketing materials, get removed by the drywaller. So you need to talk to your drywaller, tell them what you're doing, why you're doing it, and it really takes a different installation of the drywall to be successful. You can't just drive the drywall up the stud to the bottom quarter of the truss anymore. You almost have to flop it on that material so that you're not scraping it off here. Sealing of bottom plates to subfloors is a mandatory requirement. Air sealing attic accesses to unconditioned spaces is a mandatory requirement. So getting gasketed, weather-stripped attic hatches that are heavier so that they actually create a seal, and then insulating that attic access at least to the same level as the rest of the attic space or penetration is being insulated to. Air sealing and weather stripping and adjusting our door thresholds and weather stripping our doors becomes super important. Ensuring that we get good separation between garages and our houses here. Now, from a code perspective, it requires that this garage separation happens as well. What the DOE program and the Indoor Air Plus program add to this is that there's a mandatory test that happens where you have to test the separation between the garage and the house to make sure that the garage is outside the pressure boundary of the house using a blower door and this protocol there. Now, lastly, you can do the air sealing mechanisms as you build the house, or potentially air sealing afterwards using products like Aero Barrier, a new product that's come to market. It doesn't mean that you don't have to do all the air barrier portions that are required, but the air sealing portions could potentially be achieved, like the air sealing around outlets or fan housing to drywall, or can lights to drywall, duct boots to drywall. These types of things could be achieved through products like Air Barrier there. So the next section of checklists that we need to look at are the HVAC checklists here. The HVAC checklists include design and commissioning essence checklists. So the main reason why the DOE program and the Energy Star program stress the HVAC side of things, and they also want to stress this connection between the thermal envelope and our HVAC system. So if you remember the picture that showed the poorly installed insulation and the difference in the R values that can be achieved by poorly installed insulation, you'll know that our HVAC systems will not work unless our thermal envelope is ultimately working here. So the energy use dictated by the thermal envelope is ultimately the energy that we're trying to add or replace with our HVAC system here. So we're ultimately predicting our heat loss in our houses, and our goal is that we'll have normalized heat flow around our houses, so we'll have comfort around our houses. But the reality is that we often oversize or undersize our heating equipment in our homes rather than getting the right-sized equipment into our homes. So the ultimate goal of Energy Star, and hence the DOE Zero Energy Ready Home program, is to get right-sized equipment into our program. So the heating, ventilation, and air conditioning checklist begins with this design report. And so it breaks out responsibilities for the HVAC designer. They have to complete this report for each system that goes into a house. So if you have 2 or 3 HVAC systems, you'll have to have 2 or 3 reports that's specific to each system. you have to create either a site-specific design, or if you're building Plan A 100 times, you can group the designs based on orientation and BTU need for each orientation. You need to obtain the actual window insulation level and infiltration rate performance specifications for each of those designs so that it's sized properly for each specific house that these systems are going to be going into. And then ultimately you need to provide these completed checklists to not only the builder, but the contractor that's going to install the system, if it's not the same, and also the verifier or rater that's working on that house there. The design report looks like this. There's a full checklist, and it's typically used for forced air systems. It's really focused primarily on forced air systems. Therefore, if you have hydronic systems in your climate region, in your zone, only sections 1 or 2 are required sections, although sections 3 through 5, sections 3, 4, and 5 are highly recommended, and they can significantly improve the performance of hydronic systems or alternative HVAC systems that might be used in those climate zones there. Section 1 is ultimate design review. Section 2 deals with ventilation. Section 3 is about room by room heat load calculation, so getting the right load for the house, how you select the equipment, and then ultimately how you distribute that load is Section 5 here. So let's look a little bit more closely. If you are doing a hydronic system, there are exceptions that are detailed out in this table of what you need to do and what you don't need to do. So for example, if you have an air source heat pump as your primary heating system, then you do need to follow this checklist. If you're using a boiler-fed hydronic system, you don't necessarily have to have a certified installer or HVAC contractor that's installing the equipment and commissioning the equipment there. The design reports here. So this is the design report. Again, it's an overview here. It asks, who's doing this work. Are you doing a whole house design or just designing a partial system for that? Are you doing a site-specific design? Are you doing a group design? Those types of questions that need to be answered in this section of the report. Section 2 deals with whole house mechanical ventilation. So we'll break that out a little bit. We're first talking about airflow in that system there. And the airflow is based off of the ASHRAE 62.2 standard, which is a standard for whole house controlled mechanical ventilation as well as spot ventilation in our houses. And it's specific to single family homes and multifamily structures that are 3 stories or less. And that's why these programs use the ASHRAE 62.2 standard. This checklist allows us to use exhaust, supply, or balanced ventilation systems in our houses here, and they require that they be sized properly for the specific house. So just like code, you can either use this table or this formula to size the mechanical ventilation system in your house for whole house controlled mechanical ventilation. If you use the table for a 1,500 square foot house, you'd come up with 75 CFM. If you use the formula, you would come up with 52 CFM of air that's needed for ventilation. So what you're seeing is that most designers, most third parties use the formula to right-size the equipment, right-size the ventilation system for their house. Now, again, you can use a supply, exhaust, or balanced ventilation system. The supply ventilation system uses a dedicated fan or potentially the furnace air handler if you're using a furnace with some type of control to supply air to the house. You're slightly pressurizing the house when you use the supply ventilation system. which means that if you have atmospherically vented appliances, you don't really have a chance to backdraft your equipment, but you do have the possibility of warm, moist air that's inside the house being pushed through the building assembly, because supply and exhaust ventilation, generally speaking, utilizes holes in the building envelope to achieve its ventilation requirement. However, you do have control, because we know that air in equals air out, and you're setting that ventilation system at a specific rate and a specific runtime. So you have control because you know how many CFM are going in and out. You just don't know exactly where they're going out, and you have predictability because you know how long these ventilation systems are running. This supply ventilation isn't used a lot in Colorado, but we have a pretty forgiving climate here, so it can be used. When we see it in Colorado, it's usually set up like this on an HVAC system that's forced air, where you have a duct from the outside to the return side of the system and some type of controller that's running the air handling unit there. But we also are seeing more and more of these inline fans being used as well. And this is an example of an inline fan going to a ducted system to utilize the ducted system to distribute air to the house. The picture on the left is another type of supply side ventilation system that's using the air handler to pull air through that return back to the furnace there. Exhaust ventilation systems depressurize houses. Again, we like them in our drier climates because we're pulling drier air from the outside through those holes in the building envelope. Again, we have control and predictability because we know how much air is moving through our building envelope to ventilate that house, and we know our run time. So we have control and predictability. This is a very cost-effective system, especially production builders are gravitating to exhaust ventilation systems because of their cost effectiveness. Exhaust ventilation systems can be used as a single point or multi-point exhaust system. The exhaust system removes pollutant indoors from the to the outside, and exhaust fans can provide local exhaust in our bathrooms as well as whole building exhaust systems. We're also seeing exhaust systems being used in conjunction with conditioned crawl spaces to ventilate a crawl space and a house simultaneously. So that's an interesting solution there as well. You can also see other type of hybrid exhaust systems where you tie an exhaust system with a duct or known opening to the outside. So instead of pulling air from unknown sources through our building envelope, you have a source to location where you're bringing air in from the outside. Other type of hybrid systems could look like this, where you have exhaust and supply systems that are using the benefit of normal heating and cooling cycles to use a supply ventilation system. And then when the system isn't heating or cooling the house, you switch over to an exhaust ventilation system to make up the additional ventilation that might need to happen to that house. So there are a variety of different hybrid systems as well. Now, balanced ventilation systems use pressure neutral systems. They work in all climates. There aren't backdrafting issues. You do get great control and predictability, and you generally know where the air coming in and out of the house is happening. So from a building science perspective, it's probably the best choice, but it's also an expensive strategy there. Now, a balanced ventilation system using an HRV or an ERV has air streams that are exhausting air from the house while simultaneously bringing air from the outside into the house. And they runs it through a core that's shown on the right side of this slide, just to be an example of how the air in these two air streams never physically touch each other or exchange, but they can exchange heat and moisture through these cores from one to the other there. So a heat recovery ventilator, again, pulls fresh air into the home while exhausting stale air out of the home. It is able to recover heat out of that air that's being exhausted out of the house and move that heat into the fresh air coming into the house. They're about 70% efficient at doing that there, and it works really, really pretty well there, especially in cold climates here. Energy recovery ventilators typically have been thought of as being used only in humid climates, but we're seeing them move into drier climates as well now. Depending on the season, they can move moisture in the airstream that has less moisture into the airstream that has that has more moisture into the airstream that has less moisture, depending on that. Again, more to less. Everything from moisture to energy moves from more to less, and that's what this system is doing as well. It uses this entropy transfer mechanism in order to do that there. Regardless of the system that you're using, you have to have controls, and Energy Star and the DOE Zero Energy Ready Home program require that the controls are labeled as well, which code currently isn't doing. You have to be able to override the control. The control has to be obvious for these programs, and if it's not obvious, it has to be labeled. So if you're using any type of toggle switch control, you'll see how it's labeled here on the right side of this slide. This controls the ventilation system. We recommend that you don't turn it off, because ultimately the ventilation system only works as well as our education to the occupant to ensure that they don't turn off the system. Because in essence, code and these programs allow that potential. But we want to ensure that they don't turn it off, so label your systems and label your controls. The programs go a step further with regards to air intake. They ensure that you have these exhaust ports and inputs present, but you also want to make sure that you're not getting pollutants from outside back into the house. So they need to be installed properly here. Additional ventilation requirements include motorized dampers. If you have an intake from the outdoors to the return side of the furnace, for example, it needs to be dampened with a motorized damper. And it also says that the fans that you're using to ventilate the house have to meet a sound requirement or a zone requirement. And those zone requirements are so low and these fans are so quiet that the object is that the majority of the time people want to turn off or override a ventilation system is because that ventilation system is loud. And if it's loud and you're using these low zone products or low sound rated products, it means ultimately that these systems are installed incorrectly, and that's what's causing the noise. So it should be notes to fix the system rather than override the system here. This also becomes important if you choose to ventilate in a non-traditional way, for example, using a kitchen hood as your ventilation mechanism for the house. That's allowed, but you have to have a low zone fan, which is harder to find for a kitchen hood, or use a remote blower for those types of intakes as well. Okay, so the next part of the HVAC design report is the room-by-room heat load calculation. Now, this is mandatory if you're using a forced air system. It's not mandatory for other systems. It's highly recommended here. And one reason it's highly recommended is because the design of our HVAC systems generally happen early on in the process, usually pre-construction for sure, but ideally in the design integration process that we talked about last time here. So if we want to make sure that our systems are going to work, we have to make sure that we verify the installation of our of our insulation and air barrier systems in our house, and that what we used as our design assumptions are actually being carried out for wall R values and U values that the right windows were installed, that we're going to get the right house tightness installed there as well. So we're trying to avoid poor installation of our duct systems, of our hydronic systems, to make sure that these systems ultimately perform. So this design process includes calculating the heating and cooling loads, which is important for all types of HVAC systems, selecting the right equipment, which is important for all types of HVAC systems, and then ensuring that our systems deliver their heating and cooling energy to the right rooms in the right way consistently. So again, doing that verification process of all the R values and U values around our thermal envelope, is it there and does it work the way it's installed, is super important before we do our heat load calculation. But our heat load calculation is trying to determine how the energy is moving in our houses from more to less, in the same way that energy moves from this ice chest from higher temperatures regions to lower temperatures until an equilibrium is met and the ice ultimately melts, or the coffee is drunk or cooled off so an equilibrium is met. So energy always moves from more to less, so we get a heating load and a cooling load depending on which direction the heat is moving in or out of our houses here. The design report moves on to equipment selection as the next part. Again, this isn't a mandatory requirement for hydronic systems, but is highly recommended there. Ultimately, what we're trying to do is get that heating and cooling load using our manual J, and then size our systems according to that heating and cooling load. So the manual J describes every component in the thermal envelope, basically the R values and U values around that thermal envelope, and uses infiltration and ventilation requirements to determine how many BTUs of heat loss or heat gain are happening in that house, giving us a room-by-room heat load calculation. It also is dependent on the design conditions for your specific location there. The interior design conditions and temperatures are defined by code, so you'll have to go back to code to get those. It's basically 72 for the cooling load or heating load. I'm sorry, 72 for the cooling load and heating a minimum of 75. I'm sorry, 72 for the heating load and 75 for the cooling load would be our interior design temperatures. The exterior design temperatures are based off of the code that uses the ASHRAE standard there, but basically what it's saying is that 1% of the time the design temperature will be hotter than the cooling load or the cooling temperature that is designed to by ASHRAE, and that only 99% of the time the heating load or the heating temperature will be higher than what's called out by the design temperature that's defined by ASHRAE in code there. So in Denver, for example, the heating load or the heating design temperature is 3 degrees. The cooling is 91. So 1% of the time the heating temperature goes lower than that, and 99% of the time we don't exceed 91 degrees for the cooling design temperature here. So you need to define what those temperatures are in your particular region for your design conditions there to get a proper HVAC design for your systems here. Ultimately, this step is very simple. What you're trying to ensure is that the capacity of the equipment that you select meet the needs of the load for your particular building. Our ultimate goal is not to undersize or oversize our equipment there. We don't want undersized clothing. We don't want oversized clothing. We don't want undersized equipment or oversized equipment. We want right-sized equipment. And this is equally as important for forced air systems as it is for any other system. And therefore, this step 3 is highly recommended for all systems here. Now, the duct design is really primarily a duct forced air system requirement, but we do see that hydronic systems and other delivery systems for HVAC systems are not designed well and not implemented or installed well. So from a duct system perspective, we want to ensure that our furnace plant is duct with a 14-inch duct, a 12-inch duct, to a 10-inch duct, to a 6-inch duct, and it's able to deliver 104 CFM out of that register while delivering all the other air outs to the other locations in the house. In the same way, we want to make sure that each zone of a hydronic system or each zone of a air source heat pump are able to deliver the energy from its source to the particular room in its proper fashion. And that's happening is being ensured if you follow this step in the program requirements here. If you do use forced air systems, another requirement that's additional set by the DOE Zero Energy Ready Home program is that the duct systems are located inside of the building thermal envelope. So there are a variety of ways to ensure that by changing our thermal envelope or just planning properly there. There are some exceptions that you can do. Up to 10 feet are allowed to be outside the building envelope. There's some dry climate specific exceptions that you can see below. But in either case, the HVAC equipment itself must be located inside of the thermal boundary of the house. So here's an example of here. We have an HVAC system that's servicing, this is a forced air system. In this case, all the ducts are outside the building envelope, but the mechanical system has been located inside the building envelope. So this is what you would have to do as well as ensure that your equipment, heating and cooling equipment, is located inside the building envelope of the system. Now, the last of the HVAC is these commissioning reports that are looking at, again, heavily detailed with or heavily focused on forced air systems here. The commissioning checklist requires that a contractor be credentialed by an oversight organization, that one checklist be completed for each system that's installed in a house, that complete checklist for each system along with the corresponding design report be retained by the contractor and distributed to the builder and the third-party verification organizations here. And you can find out more information on credentialing at this website, at the EnergyStar.gov website. So the HVAC contractor, again, must be credentialed. The rater must sign off on these inspection checklists as well. And you can go to the EnergyStar websites to find out more information about the HQIDOs, which is the HVAC Quality Oversight Organizations. It turns out that there are only two quality oversight organizations. One is based out of ACA, or the Air Conditioning Contractors Associations of America. The other is based out of a group called Advanced Energy here. And again, I believe you only have to use a certified credentialed contractor if you're doing a forced air ducted system with traditional air conditioning in that house. I don't know if there are any credentialed contractors in Summit County or our higher climate zone areas, but you can go on the EnergyStar website and search for contractors to see if they are credentialed or not. Now, the design review has to also happen from the rater. So the rater's looking at this design review checklist that the contractor or the designer did and looking at these different categories there. Then the rater is also looking at the field HVAC checklist and looking at the equipment and other installation criteria that are done there. This can be done in two paths now with revision 10. You can use this insulation or this HVAC grading protocol that's just been released, or you can use the normal pathway that's been around for years now, this HVAC credentialing pathway. Again, this is highly focused on forced air systems here, so we're not going to spend tons of time on it, but the new HVAC grading system basically goes through a series of commissioning exercises, and it's sequential. So if it doesn't meet the tolerances and grade in test 1, then it can't move on to the next one. So it has to be sequential there. So you're looking at total duct leakage, you're looking at blower airflow, you're measuring the wattage of the blower fan, you're verifying the refrigerant charge in these types of systems here, and then you can give full credit to this. And this ultimately can add or reduce HERS index points to the system in the same way that grading insulation can. Again, it's for a forced air system, not a hydronic system here. So if you choose path A or B, you have to ensure that the manufactured model numbers on the equipment match the design reports. So the installed equipment matches what's designed for that house. You have to measure external static pressure if you have a forced air system, and you have to collect and store the HVAC design commissioning checklist there. The checklist for step 2 is duct installation. Looking at that, the HVAC checklist now for the DOE program requires that all the ducts are inside the building envelope. You have to do room pressure balancing, third-party verification of duct leakage testing for both total duct leakage and duct leakage to the outside, which is an additional requirement beyond what code would normally require there. But again, it's for ducted HVAC systems. Duct leakage testing is looking at the whole duct system. It's looking at total duct leakage testing, which we're not going to go through, but these are the basic steps that you go through to perform a total duct leakage test. It's just not as pertinent in our mountain community, so we're not going to spend that much time. But you'll have access to this slide, or if you have any questions about how a total duct leakage test happens, you can give me a call or ask a question. Duct leakage outside testing occurs, it has to occur at a final stage of construction because you have to use a blower door and a duct blaster or duct leakage testing device running simultaneously to do this test. Again, this is the protocol for how you do this test there. So if you have any questions on that, please let me know. Sealing of duct systems has happened for years and years, just using liberally applied mastic on our systems, but there is an AeroSeal product out there that can seal duct systems as well if the system isn't tight enough, or if you want to start from the onset using an air sealing system. There are different ways, in essence, to seal up those systems, but that they're tight is super important. The rater also needs to do some measurement or verification of whole house mechanical ventilation flow through those systems. This is a flow box that measures the CFM that's going out of an exhaust ventilation system. The ventilation system needs to be within either plus or minus 15 CFM or plus or minus 15% of the design flow rate for that particular house. We have to assess the ventilation control requirements for that, and the outdoor-indoor motorized dampers have been installed. If motorized dampers have been installed, it's often because you're using a forced air system, and if you're using a forced air system, you have to have an ECM motor on that furnace blower there, and so you would have to verify that. You have to verify the sound requirements or the zone rating of intermittent fans that are used, or if you're using an exhaust ventilation system, that it's a one-zone continuous running ventilation fan in that system. Other exhaust ventilation fan requirements and air inlet requirements you need to verify. The fan inlet requirements are important to know, especially in high snow load zones. You have to ensure that your air inlet is at least 2 feet above ground so that it doesn't get covered by snow. And then the 3-foot, 10-foot rule, so you're not bringing back in exhaust products that might be coming from the house, aren't going back into the house through the ventilation inlet fan. So there's that 3-foot, 10-foot rule that you should be aware of and probably already know about here. The Rater HVAC checklist, section 4 for local exhaust. Again, you have to look at the sound rating, and if it's an Energy Star qualified fan, this is one of those requirements that is addition to Energy Star. If when coupling the program with the DOE Zero Energy Ready Home program, exhaust or ventilation fans have to be Energy Star qualified fans, and they have to be proper sound rated fans as well. Requirements for local exhaust is basically following the requirements of the code. So the local exhaust for kitchen hoods, minimum requirement, 100 CFM fan if it's running intermittently, 25 CFM if it's running continuously. For bath fans, they have to be able to push 50 CFM if they're running intermittent and 20 CFM if they're running continuously. With these programs, you also have to test the flow through these fans, which we'll see in a second here. They also have to be installed properly and discharge everything to the outdoors here. And then the exhaust openings, that 3-foot, 10-foot rule applies to these exhaust openings as well here. Our kitchen exhaust fan is supposed to be exhausted to the outside as well. There is a loophole in the IRC, so you'll see some recirculating fans out there. However, for the Indoor Air Plus program and the DOE Zero Energy Home program, that fan does need to be ducted to the outside, so that's an additional requirement. And at a rough stage of construction, we need to verify that you're using at least a 6-inch duct to vent that from the outside. And that's to ensure that you can at least get 100 CFM up and out of that house there. So you want to make sure that you specify that and that you're getting that installed at that rough stage of construction. Sorry, just taking a quick drink. Dryer vents are also super important for moisture control, to make sure that they're ducted all the way to the outside and that they're hooked up properly to our dryer equipment in the houses. Duct installation is governed by the IRC, but is pertinent to these programs to ensure that all the joints are sealed, ideally with mastic, but you're running moist air. You're trying to get moist air from the house all the way to the outside. You don't want that duct to be leaky. And then another thing to think about, as shown in the picture in the lower right-hand corner, is that sometimes when you're screwing the duct to a fan, you might impinge or restrict the movement of the internal fan damper. That can cause that fan to be quite loud and also restrict the flow of air through that fan from inside to outside. So look at those things as well when you're verifying and specifying. Filtration is step 5 of the HVAC checklist. For the Energy Star program, a MERV 6 filter is required. For the DOE program, because of the Indoor Air Plus component, you have to go up to, at a minimum, to a MERV 8 filter be installed in these systems. The filter access needs to be gasketed and closed and sealed shut. So the picture on the right is of a filter access that is not gasketed. You can't have an access panel like that. The picture on the left not only shows a higher MERV filter, but you can see that the filter slot is gasketed and has a latched door on it. So those are the types of doors that you want to see in your filter slots. All air that is coming into the house is required to be filtered. So if you're not using a forced air system, but some other type of whole house ventilation system, that air needs to be filtered with a minimum MERV 8 filter installed here. Combustion appliances, furnace, boilers, and water heaters are mechanically drafted or direct vented, i.e. basically they need to be sealed combustion systems. We're seeing that in the case of furnaces and boilers and whatnot. Sometimes in the case of water heaters. You still are seeing direct vent water heaters and not sealed combustion water heaters. That is allowed by the program, but from an indoor air quality perspective, sealed combustion appliances are what you really want there. You notice on the top picture of the furnace venting that they are taking the combustion air from the house instead of running that PVC vent pipe all the way to the outdoors. That is not allowed really by code or by these programs. So we see that sometimes here on the Front Range. I just wanted to point it out. So if you see that or you're thinking of installing like that, you need to know that that's not allowed by the programs, because that is not sealed combustion. It's not a sealed combustion appliance anymore, or a direct vent appliance, really. Fireplaces need to be mechanically drafted or direct vent. So it's really hard to have a natural wood burning fireplace in these houses there. If unvented combustion appliances other than cooking ranges or ovens are located inside the home's pressure boundary, then you have to do a ResNet combustion safety test on the house there. So there is an exception that's allowed, especially this would be especially important if you decide to try to design with a wood burning fireplace in the house. It has to be able to pass a combustion safety test there, which is not necessarily easy to do. Okay, so the last checklist that we're going to be talking about is the Builder Water Management Checklist. The Water Management Checklist is the builder's sole responsibility. It is not something that gets third-party verified unless the builder wants it to be third-party verified, and it's strongly recommended that you consider to do that. One reason it's strongly recommended is that it's additional quality assurance. And the second reason is that you might be able to get a break on your insurance if you demonstrate to the insurance company that you're going through third-party verification and quality assurance of these features in the house. The features that we've already verifying are part of that, but these water management features are the second component of that. So it's the exclusive responsibility of the builder to ensure that these features are met and that they are constructed properly to meet these requirements. The builders are required to incorporate these items that are on these checklists within their construction documents, within their scope of work documents, and within any inspection requirement that might need to happen there. Excuse me. You are allowed to have your building superintendent verify these items, or you can, again, contract with a third party to verify that these items have been installed. If the EPA determines that a home was certified and that these requirements were not met, you do risk the potential of losing certification for that house. And, you know, obviously the potential of not being in compliant with the code in your jurisdiction up in Summit County there. So it's super important that you take this equally as important and that you realize that it's your responsibility as the builder, and that those third parties that are on the call today, that you relay that information well to the builders that you're working with here. Now, the first part of this is about water management, site and foundation control. So ultimately getting that water off our building, drained down, and then away from the site here. The IRC happens to regulate a lot of these things. So you can go to the IRC for some examples if you need to about what you need to do to install the proper drainage systems away from our houses. The checklist also looks at gutter systems, ensuring that the gutter systems and the compaction of soil around the site to ensure that we have the proper slope of soil away from the house, and that the gutters are routing things, moisture down and away from the house and away from the roof, or down from the roof and away from the house at least 5 feet here. The IRC also talks a lot about damp proofing and waterproofing strategies. using drainage systems around our houses is a requirement, and it's a requirement of the checklist as well. Drainage systems are also talked about in the IRC and a requirement of our checklist as well. So you'll see potentially sump pits there. They can be in conjunction with radon systems or independent. If there is a sump pit located in the home, they have to be airtight sump pits. So you'll see that the lids are sealed to their surrounding areas, and that any penetration through the lid is also sealed as well here. This is just pointing out radon system in conjunction with that. Capillary breaks are called out specifically on this checklist. So capillary breaks are trying to deal with these hydrophobic materials which absorb water and might transport it against gravity up into our building assemblies. There are basically two approaches to deal with this. We can use damp-proofing membranes that we just talked about for our foundations, or we can install capillary breaks. And capillary breaks are required by the program, especially under slabs and slab foundations here. So capillary break is trying to stop the movement of moisture up through the pores of concrete specifically, and then up further into our house to keep that moisture out of our houses here. Remember that sill seal is a capillary break. It doesn't do a great job at air sealing our houses there, primarily because our foundations aren't often level, and we end up shimming those foundation sill plates in order to create a level framing surface there. So capillary breaks can be installed not only at the sill plates to foundation connection, but at the stem wall to footing connection as well, and then underneath our basement slabs or other slabs that might be installed in that house. If it's a slab on grade, crawl space slab, or basement slab, we need to get a capillary break below that basement slab, and that is a mandatory requirement of the code here. It can be done with foam boards, it can be done with poly. We want to make sure we have that gravel underneath there as well, because we'll see next week, part of the Indoor Air Plus program is a radon system also being installed in the house that relies not only on that gravel for drainage of our foundation, but also as an airspace to pull air out underneath the foundation before it has a chance to get into the house. Unvented and conditioned crawl spaces, the real connection here, it's governed by the IRC and whatnot, but the real connection here to the checklist is that solid vapor retarder over the dirt floor that's sealed to the perimeter foundation walls, seams overlapped and sealed to any monoposts that are in those systems here. And that part of the vapor retarder is called out specifically in the IECC. That vapor retarder installation is called out in the IECC, so you can look there for reference to that, as well as the IRC and the program documents as well. Vapor retarder installation. Here, the main thing that the program is looking at is this exception. The exception says that basement walls should not have a Class 1 vapor retarder on it. It continues to look at a below-grade portion of other walls and then tells you how you can use a Class 3 vapor retarder. But from a programmatic perspective, we need to look at this basement wall exception here. So if you do basements, if you do crawl spaces, you want to make sure that that foundation wall isn't covered with a Class 1 or 2 vapor retarder. And the picture on the right here is showing a perforated vinyl fiberglass blanket, covered vinyl. It's a perforated vinyl covered fiberglass blanket. That perforation allows permeability, so it allows drying potential of that foundation, concrete foundation wall to dry inward through those holes. Those holes are small enough, however, that that vinyl can also act as an air barrier on the fibrous material that is air permeable. So it's a decent product to look at if you're not going to insulate on the exterior of your foundation, or you're not going to use foam board material on that foundation assembly. Water management wall assemblies. The first thing it's talking about is ensuring that we have proper weep screeds when we're using stuccos or bricks or stone products, and really encouraging a rain screen technology there so that we can get our sacrificial coats to these cementitious products there, and we can get an air gap for drying potential of our wall assemblies and for water to drain past the assembly and then out through the weep holes that we need to make sure are present in those assemblies there. It talks, that section of the checklist also reiterates what the code is looking at in IRC, the installation of weather-resistant barrier systems on our house. That's a requirement there. Flashing details, I guess I should mention here, again, drainage screens, rain screens and drainage spaces aren't necessarily required by these programs or codes, but are highly recommended to consider, especially in your climate zone. Flashing techniques are required by the checklist as well. So the key to successful flashing details is in the following, basically the shingle fashion flashing of windows and other openings in our houses there. So we want to make sure that we follow these details. We get things flashed when we have penetration through our wall systems and our window openings. Water management roof assemblies. Now there's some caveats here in dry climates, but in cold climates, it's generally thought to follow these specifications completely. Footnote 4 is where you'll see exceptions for dry climate zones. So you can look at that, but again, I think in your climate zone, it makes most sense to do these things. So the first thing that's called out in that checklist is dealing with roof assemblies that abut wall assemblies, and ensuring that we get proper step flashing and kick-out flashing in those assemblies so that we don't get an overload of water onto the walls below those connection points there. So there are a number of details out in the marketplace to ensure that you get proper step flashing that's integrated with your roofing material, and then proper integration of our weather-resistant barriers with other flashing from wall systems to roof systems, and then proper kick-out flashing there to ensure that water isn't going to flow onto the walls below there as well. Gutters are requirements, again, taking that gutter away from the house so that the gutter isn't overloading water onto the foundation, and then we get capillary action happening again into our houses. So we can divert water using a downspout that takes it at least 5 feet away from the foundation, or we can put exterior foundation drain systems into our houses, or we can use some type of cistern method to route water away from our houses there. But ultimately, the goal is ensuring that water is routed down and away from our structures there. Roof and valley and roof and deck flashing details. This is the section that could be exempt in dry climate zones, but probably makes sense in high snow zone areas, that we get these valley flashing details done. We get roof penetration details done at our roof decks, that we get flashing at our eaves up 2 feet from the wall section of that house. So basically, usually somewhere around 4 feet from our eave up, that we have this type of eave flashing, additional eave self-adhered flashing happening at these locations there. But those are requirements of the program. Now, water management building materials is trying to ensure that no wet surface in our house or easily wetted surface in our house is using a moisture absorbent material. So basically no carpets in our bathrooms, in our kitchens, in our laundry areas. there. It's surprising, at least here on the Front Range, how often you come across carpets in bathrooms and whatnot. Making sure that we do our moisture-resistant backer board installation properly at all bathtubs and shower pans, and all of those things are done well and properly there. Proper vapor retarder installation. If you're going to use a Class 1 vapor retarder, it needs to be installed properly so that air isn't going to bypass it there, so that it's able to stop the moisture transport by diffusion, but unfortunately it also has to stop the vapor transport by air leakage as well there. So it becomes part of your air barrier assembly. Thinking of the whole wall assembly as that air barrier there. Building materials with visible signs of moisture damage cannot be used in an Energy Star qualified house there, so you need to make sure that that's being taken care of, and the moisture content of wood here. Now this is a little bit duplicative of what is required in the Indoor Air Plus program, but you can't cover up wet materials that have moisture content greater than 18% with drywall. You have to give them time to dry out properly and dry out below 18%, ideally even below that level there. Corrosion-resistant condensate drain systems have to be installed in our systems. We don't see a lot of, well, I guess we do see HVAC systems that are installed in attics, and that's what this is showing here. So you want to use a plastic drain system so that it won't corrode and create and potentially leak in our systems here. Okay, so right on time here. That was a lot of stuff to go over there. So to conclude, what ultimately the DOE Zero Energy Ready Home program is trying to do is leverage the details and not create new details, but leverage the details of the Energy Star program to achieve a rock-solid thermal envelope that will make sure that you're ready to be zero energy by the time you install PV systems on the house. We want to ensure that you have great air control systems, thermal control systems, and moisture control systems in our house so that we get great control and predictability of airflow, thermal flow, and moisture flow in our houses. Solid, rock-solid mechanical systems as well. That's why all the design checklists and HVAC commissioning checklists are installed. It's highly important to think about design integration of these HVAC systems with the thermal envelope that we not only design for and expect to be installed, but what's verified out there that we actually are getting what we're inspecting there so that these systems will work, that we properly size these systems, that we get the right loads for these systems, and we ultimately get the proper installation of these systems. And one way that we try to ensure that is through third-party verification programs that are associated with that. And the DOE Zero Energy Ready Home program really adopts that third-party verification that's required by the Energy Star program as well. So I often talk about this from a code perspective, but from a program perspective, I like this statement from the Dalai Lama that says you need to learn the rules so you know how to break them properly. To me, that basically means that you've got to download these program documents from the Energy Star program and from later on here, the Indoor Air Plus program. You need to spend time with these checklists and not only read the checklist items, but read the corresponding footnotes. A lot of the mandatory requirements are embedded in the footnotes, not the checklist item there. The better you understand these requirements, the better you'll know how to get flexibility in utilizing these requirements to achieve your ultimate goal of a code-compliant house that can be certified with the Energy Star program and the DOE Zero Energy Ready Home program. And then later on, we'll be talking about the Indoor Air Plus program. So thanks again for spending a couple hours with me today. It's a lot of stuff that we've gone through. Again, it's just an introduction. You need to spend your time with those checklists to learn this even better. If you have any questions please don't hesitate to throw them out now, or send me an email or call me if you want to. Any way to communicate is a good way to communicate. Thank you.
Thanks, Robbie. That was very informative. You covered a lot of material in only 2 hours. Yeah, so we're going to go ahead and open it up to questions now. Feel free to unmute yourself or write in the chat, and we'll stay in the line for another few minutes. But thank you for your time, everyone.